Greetings, I'm Doc Harris. I certainly hope you know that by now. And I'm recording these videos for two reasons. First, obviously, the coronavirus is kind of disrupting everything right now. And so in preparation for when they may or may not have us do online classes, I figured that I'd get a head start on these. And I wanted to record these so that you have a study aid in the future that you can use whenever, good times or in bad, to review the material that we are going over in class. As you know, I like to ask a lot of questions in class. And some of you actually like answering those questions, and I thank you for that. Harder to do that on video, but I'm going to provide plenty of opportunities in this video to pause and think about what we're doing. And I want you to actually do that. When I tell you to pause and think, or when I ask you a question in this video, in any of these videos, I hope that you actually do that. Pause and think. Because that's how you actually learn, when you actually start doing it. So I'll give you those opportunities, and we will learn about momentum today. If you're wondering why there's a starship in the corner, well, that's because my webcam was cheap, and so it automatically defocuses very, very quickly unless there's something interesting for it to look at. So that means we're going to have weird things on the sides of the screens, most likely, so that the camera has something to enjoy. Anyway, we're going to be learning about momentum today. Momentum is the next big thing in Physics 1. We started with kinematics, the study of motion, and we went to forces, understanding how motion and force relates to acceleration. And then we went to energy, and now we're on momentum. You'll probably be using momentum quite frequently as you go through your education, so it's a good thing to learn. Momentum is expressed with a lowercase p that is a vector. That means that the direction matters. And that is equal to the mass of the object times its velocity. And again, direction matters here. The units for momentum are exactly what you would expect given the equation for it. The units for mass is kilograms. The units for velocity is meters per second. Thus, the units of momentum is kilograms meters per second. This quantity will often get conserved in problems that we're going to look at. That's not always the case. We'll actually start with problems where it isn't necessarily conserved, and then we'll move on from there. I'm going to give everyone a few seconds to go to Canvas and open up the lecture slides 113_momentum1. We're going to be going through a lot of those slides today, so it's not a bad idea to have those available to you as we're looking through it. All right, if you go to slide 5, you will see the first example problem, calculating momentum. It says, what is the momentum of a 900 kilogram car moving northeast at 20 meters per second? So it's never a bad idea to write down what we know and draw it out a little bit. Of course, we can look at 900 kilograms, 20 meters per second. You see the equation right there. Plug and chug, and I want you to pause for a second and do this in your head without a calculator because it's sometimes important to be able to do that. All right, well, I hope everyone has solved it. The answer, 18,000 kilograms meters per second. Okay, what am I missing? Pause and figure out what I'm missing. And I hope that you saw that the thing that I'm missing is that I needed to say that it is going northeast. Every vector answer has to have a number, units, and a direction. An idea that's very closely related to momentum is impulse. And impulse is denoted with a J vector. Again, very important which direction this impulse is taking place in. And so we have to remember that it's a vector. The vector J impulse is equal to the change in momentum of an object, which delta anything is, of course, the final minus the initial of that thing. And We can also express the impulse J as F net delta t. So the impulse on an object is equal to the force on that object, the net force on that object, times the time under which that force was being applied. We've seen very similar things with this very recently. We saw that E is equal to, delta E is equal to W, and W is equal to F d cosine theta. So we had this other instance where we had a change in something being equal to a different thing, and that different thing being equal to something with a force, times something else, So here the impulse is related to the force times the time. Here the work is related to the force times the distance. So use those skills that we developed in those previous energy sections and apply that to when we're using impulse. We can also express impulse as an integral. This impulse integral is taken from some time to some other time, and it's integrating the net force over time. So you can see that if the net force is constant, then integrating over time is just going to get you F net delta t. So these two equations are very consistent with each other. This is very useful when the force is changing, and this is very useful when the force is staying constant. All right, get to slide 8 in this PowerPoint presentation. This is where we're going to start doing some examples. So the first example on using impulse, you throw a 0.25 kilogram ball at a wall at 8 meters per second. It bounces off, coming back at 6 meters per second. So we have a wall, and we've got a ball that comes in, hits the wall at 8 meters per second, bounces off the wall at 6 meters per second, and we need to find the impulse of the wall on the ball. First of all, I want you to pause and consider, what are most people going to get wrong on this problem? There's one thing that they're probably going to get wrong when they start trying to solve this problem. The equation that we're going to use to solve it, J is equal to delta P, which is P final minus P initial. Well, we need to also remember that P is equal to mv. What do you think people are going to get wrong with this? I'll give you a moment to pause and consider that. All right, I think that most people will get that this should probably be negative the direction of that. The way that I've drawn it, the 8 meters per second is going to the left, and so we're probably going to just label this 8 meters per second as being a negative value, and this 6 meters per second as being a positive value. Well, let's go ahead and solve this to find the impulse of the wall on the ball. If I want to find the impulse, I need to find the change in momentum. If I want to find the change in momentum, I can take the final momentum minus the initial momentum. So all I need to do is plug in the momentum equation in here. So J is going to be, well, it's going to be the final momentum, mv final minus mv initial, as you can see. And we need to remember directions, especially important in this kind of problem. So J is going to be the mass of the ball. I said that the mass of the ball was 0.25 kilograms. So we can multiply 0.25 times, I'm going to factor out the masses, so I just have V final minus V initial. V final is the 6 meters per second, I'm going to leave that as positive, so positive 6 minus V initial, well, V initial is negative 8, therefore this is 0.25 times 6 plus 8, which is 0.25 times 14, which is 3.5. What do you think the units of this are going to be? I'll give you a moment to pause and think about that. Well, the units of this should be the same as the units of momentum. And the units of momentum were kilograms meters per second. Now, what else do I need? I need a direction. The direction of the force of the wall on the ball, sorry, the direction of the impulse of the ball, of the wall on the ball, well, the ball had to change from going to the left to going to the right. Therefore, it had to have a substantial amount of something pushing it to the right. And so we can presume that in this case it's to the right, which the lack of a negative sign there would also indicate that it's to the right. Moving on through the slides, we get to the next part B of this example. If the collision of the ball with the wall took 0.01 seconds, so t is 0.01 seconds, what was the average net force on the ball? Well, for this, we probably need to remember that the impulse, which is equal to the change in momentum, is also equal to the net force times the change in time. So all we need to do to find the average net force on the ball is to plug in what we had here for our impulse, and we see, and then plug in our time as well. Then we can see pretty quickly 3.5 kilograms meters per second rate is equal to the net force times 0.01 seconds. And I hope that you can all do this in your head as well. What happens when you solve for F? You should get 350 newtons. And this is going to have the same direction that we had before. And that makes sense. If the ball hits the wall, it's going to bounce off. There had to be a force that was pushing the ball off the wall to the right. Next one, find the acceleration of the ball over that 0.01 seconds. Well, how are we going to find the acceleration of this ball? There's multiple ways. I want you to think of two different ways that we could find the acceleration of this ball during its contact with the wall. Have you thought of two different ways? I think the easiest way is to remember that the acceleration is equal to the change in velocity over the change in time. The change in velocity, well, it went from 8 in the left direction to 6 in the right direction in meters per second. So change in velocity is going to be it's going to be v final minus v initial over time. V final was positive 6 minus negative 8 over 0.01 seconds. That's going to get us 14 in the numerator divided by 0.01. Again, I hope you can do this in your head. Acceleration should equal 1,400 meters per second squared to the right. The other way of doing this, to find the acceleration, is to take the force that we just got. Up here, we got a force, we had a mass, 0.25 kilograms, F equals ma. If we take our force, 350 newtons is equal to 0.25 times A. We solve for A. We need to divide 350 newtons by 0.25 kilograms, and that is still going to get us 1,400 meters per second squared. And the force is to the right, so the acceleration must also be to the right. Finally, we need to find the change in velocity of the ball over that 0.1 seconds. And, well, I hope that you can already see that we already did that. That right there is going to be our delta V over that period of time, 14 meters per second to the right. Okay, now we're on slide 16. We're going to be looking at the impulse on a rocket. I'm sure none of you care about impulses on rockets at all, but we'll do it anyway. We've got a reaction control system, RCS, on our rocket. We've got a 4,000 kilogram rocket somewhere in space, presumably. We've got some sort of RCS unit on it. The mass of the rocket is 4,000 kilograms, and it's traveling forward at 11 meters per second. So we'll say that the velocity is 11 meters per second in the forward direction. Its RCS fires, imparting an impulse to the rocket of 8,000 kilograms meters per second to the right. So we have an impulse acting on this. And the impulse coming from this RCS thruster, it's going to be pushing it to the right. I say imparting an impulse to the rocket of 8,000 kilograms meters per second to the right. So to the right, and that means that the exhaust is coming out like that. And we need to say 8,000 kilograms meters per second. Question for you to think about before we move on. Will the x component of the velocity change when this impulse occurs? Will the x component of the velocity change? What is the current x component of the velocity? Answer that. And will it change when this impulse is applied? What about the y component of the velocity? What is the y component of the velocity right now? And will that change when this impulse occurs, when the RCS fires? Well, I hope you see that the x component of the velocity will definitely change thanks to that impulse, and the y component of the velocity will not change. That means v initial x is, what is v initial x? I hope you see that it's 0 meters per second. V final x, we don't know. We'll probably be looking for that. V initial y is 11 meters per second. And V final y is also 11 meters per second. Remember, x doesn't care about y. Things that happen in x don't affect what's happening in y. So the initial and final velocities in y should be the same because nothing affected it in the y direction. How do you find the x and y components of the velocity vector for this problem, the final velocity vector? How are we going to find the final velocity in this problem, the final x and the final y? Well, we already have the final y, so I guess we just need to find the final x. I'll give you a moment to think about a strategy that we could use to find the final velocity in the x direction. And I'll give you a hint. We need to go back to impulse is equal to the change in momentum. And notice that I'm writing in the vector signs up there always, and that the momentum is equal to the mass times the velocity, also a vector. So think about what you'd need to do to find the final x velocity in this problem. And let's go ahead and do that. Now that you've figured it out, we need to find the final x velocity. Well, we know that the impulse is 8,000 kilograms meters per second, so we can take this and say 8,000 kilograms meters per second is equal to the change in momentum, but the change in momentum is going to be the momentum final minus the momentum initial, and momentum final is going to be mv final minus, let's see, what's the initial momentum going to be? I could hear you through the screen, you're yelling 0, so we've got 0. We just can find the final velocity from that. 8,000 is equal to the mass, which is 4,000, times Vf, which I hope you can see that this is going to be 2. meters per second to the right. All right, we found the final velocity in the x direction, final velocity in the x direction. Now we can find the magnitude and direction of the rocket's velocity. We need to find v, the magnitude of v, and the direction of the rocket after this. Well, the magnitude of v is going to be Pythagorean theorem, v final, this is final x squared plus v final y squared. And the angle is going to be the inverse tangent of y over x, specifically the velocity in y over the velocity in x. So we can figure these things out. We can take the square root of v final x. Well, v final x is 2 squared plus v final y is going to be 11. Square that, take the square root, and add a decimal, so I get it in decimal format, and we get 11.18 meters per second. And then you can do this too. So we need the inverse tangent. Let me make sure that I'm in degrees right there. You know who you are. Of y over x. So we're going to have 11 divided by 2. And that gets us 79.7 degrees. And what direction is that really in? What should I say about that? I should relate that angle to something. Remember, if we're using the unit circle, we can just say that this is our plus x, this is our plus y, and all angles will be measured from the positive x-axis going counterclockwise. So a 79.7 degree angle is going to be something like that, because this right there is 79.7 degrees. So for slide, let's see, 19, the answer will be 11.18 meters per second at a 79.7 degree angle. All right, looking back at our impulse stuff, we've got quite a bit of meat that we can do with these equations right here. We see that the impulse is equal to the force on an object times some time. Often we're going to have multiple objects in one system all interacting with each other in some way, and we can look at the forces acting on all of them together. Now, we can also, what we've been doing is looking at one object at a time, finding the impulse on an object or the force on an object given a change in time for that one object. But we'll see very soon that these concepts are going to be useful for collisions. So if we take two things and collide them into each other, that's a system. Those two things are a system. And if they collide into each other, then we can find the impulse on that system of the two objects together. Just like we had all those problems with energy, with like multiple objects all having something with their energy change, we can do that here. So if you imagine two objects, for example, two cars that collide into each other, well, that's a system. The two cars together are a system. Before and after, that's one system. We can look at the force coming in from outside on that system, on the two cars, and how long all this takes. Now, if you imagine just two cars that collide into each other, or perhaps two billiard balls that roll into each other, and think about the forces acting on both of them put together. The net force acting on both of them put together. Now we're probably going to have a gravity pointing down and a normal pointing up on these things, but those are going to have a net effect of 0 in the y direction. In the x direction, what are the forces? Well, maybe there's some friction. Maybe. Well, what about wind? Maybe the wind is blowing a little bit, and that's applying a force to this. Well, we have all these options, and those could give some sort of impulse. However, A collision is often very brief. The actual period in which two things collide is a very short amount of time. And so if there are forces acting on the outside, on the system of objects, we have to multiply that by the amount of time that the collision takes. If the collision takes 1/100th of a second, or some very, very small fraction of time, well, no matter what the force is, we're going to have a very small delta t, and therefore, most likely, a very small impulse. Now, if we have a small impulse, then that means that we must have a small change in momentum. And if we take this to the logical extreme, we should be able to say that if a collision or some other event happens over effectively no time, if it takes effectively no time, or if there's no forces incoming on it, or both, then we should be able to say that J is 0. And if J is 0, then delta P is 0. Now this is a conservation of energy. Sorry, conservation of momentum equation. I was thinking about conservation of energy because it looks just like if work is equal to 0, and remembering that work is equal to the change in energy, therefore the change in energy is also equal to 0. So again, very similar kind of concept between these two things. Well, that seems like a good place for a break, so we'll be back next time to talk about conservation of momentum. Hope everyone has a good rest of your day, and email me if you have any questions.